C1, 1 minus C2, x1, 2, and then 1/4, x1, 3, look at x1, 3, so you have plus 1 plus C1, 1 plus C2, plus 1/4, you have now here 4, x1 at 4, so C1 is negative, C2 is positive, 1 minus C1, 1 plus C2. So this one is pretty much standard. It's the same thing that you can use here. Okay, very standard when you map this quadrilateral element from x1, x2 to C1, C2. Yes? So have a look. So here you have -1, x1, 1. You have number 2 is plus C1 minus, because it's below, C2 negative. And then this one here is 3 plus C1 positive C2. And then x14 is this one here, minus C1 plus C2. So pretty much standard. This one is a pretty much standard mapping technique for a quadrilateral element. So from this one to that. Okay, so have a look, they are the same. So not a problem. So that is your x. So from here, you will get now x1 with this equation here, and so on and so forth. So as you can see, they are the same, right? So this one now will be your shape function, n1. This is your second shape function. This one is your third shape function, and your fourth shape function. Because they are the same, so we have n1, n2, n3, and 4, n1, n2, n3, and 4. So you can write it as xi equal to n1, xi1, n2, xi2, n3, xi3, n4, xi4. So you can write it in this manner now, your shape function in this manner, and your x vector will be in this manner. Yes? So what about your displacement function? So your displacement function, you can simply have this one here, as we earlier solved, or as you have seen it earlier. So you will have this one as your shape functions. Okay, you have u11, u12, u13, u14. So these ones will be your shape functions. n1, n2, n3, and n4. And each related to these different displacements. So you can simply write them as u1, u2, and very standard form. So here, you will have now this one here, and then n1, n2, n3, n4, shape function. Yes? So, how do you solve for the stiffness matrix? So you've done that for the bar, you've done that for the beam. What about for a plate? So as you can see, you have now here your B matrix, taking note that your B is the derivative of that shape function with respect to x, multiplied by your stiffness matrix, multiplied by the transpose of your strain displacement matrix. So again, this equation is similar in form to what we did earlier. EDA, meaning just the thickness multiplied by the area. So it's still the volume integral. But since the thickness is constant, you can bring it out. So we have now to integrate this one twice from C1 or C1 axis and then C2. So -1 to +1, taking note of that C1, and then the other one is C2. So have a look at this one. We need a Jacobian to be able to integrate this one. Yes? So dA is dx1, dx2. And to be able to transform this one, we have dc1, dc2. So it's like a bar, but we have two axes. So it's the same in form, no change in form, it's the same. It's just that we're trying to add in more parameters here. Yes? Jacobian definitely will be a matrix. Your stiffness is a matrix. Jacobian is a matrix. Your strain displacement matrix is larger. So again, there's so many things to consider. Unfortunately for this one, we cannot get a symbolic form as what we can get for a bar and a beam. So no symbolic form. So to be able to integrate this one, you need to perform numerical integration. So have a look. What's the size of your matrix for a single element? Well, anyway, it's just a simple 8 by 8 anyway. So it's just an 8 by 8. But the procedure here is very standard. The procedure here is very standard. So all you have to do is to follow that method. So no other methods to follow. Just follow the methods that you have. Once you have the coordinates for this element, 1, 2, 3, and 4. Once you have the coordinate, just follow that procedure, nothing more. Because this is a numerical method, you're just following a procedure. And everything has been simplified using this concept here. Everything has been simplified. You don't have to perform anything, just follow the procedure strictly. Okay? So, actually, you don't really have to think. Once you know how to perform this one, it's just a process. So let's try. Let me just show you how to do that. First, you have your strain displacement matrix. Yes? So this is your equation. But you cannot integrate. You cannot get a more simpler form than this one. This is the simplest form. This is the simplest form of your stiffness matrix. So the first thing you have to do is to determine your strain displacement matrix, which is given by this one here. So shape function, what is the shape function? For a quadrilateral element, the shape function is fixed. Don't have to change. So from this one to that, your shape function is already fixed. No change. So once you have your shape function, then you have to determine your Jacobian matrix. So first is your shape function, you have your Jacobian matrix. Take the derivative of that shape function with respect to C. That is, shape function will be as a function of C. So take the derivative of your shape function with respect to C and multiply it with this Jacobian. Nothing more. It is a process. Your seniors have done it. We've done quite a number of rounds and they were able to understand it, so I don't think that it will be difficult for you. Like I said, it's just a procedure. So, there won't be change in here. So it's the same. So this one will be the same. This will be the same, and so on and so forth. So take the derivative of that shape function with respect to C1, derivative of second shape function with respect to C1, and so on and so forth. You get these values here. Okay? Very standard. It's just laborious because you just have to take those values. The next thing you have to do is determine your Jacobian. So once you determine the Jacobian, then others are just straightforward. So this is your Jacobian. So your Jacobian will determine your coordinates. Now this equation is fixed for a plate element. This Jacobian, J11, J12, J21, J22 is fixed. It's given by this equation, partial derivative of x with respect to C1, which is already given here. Because you have already your shape function that is fixed, so you can take the derivative of that shape function with respect to C. And then just put in, these ones here are your coordinates. This is where that values or locations come in to the picture. So as you can see, for this one here, okay, for this one here, you don't see any coordinate of the element. It's called C2, C1. But when you go to the Jacobian, you will see that this is where your actual number will be coming in. So you don't do anything, just put in the values there, and your Jacobian will take into account the different parameters there, the locations. Your 0.1, 0.2, 0.3, and 0.4. So once you solve that, then of course it's straightforward. Okay, so you get your J11, J12, you get your J21 fixed, and then J22. So once you get that, you go back to your equation, which is this one here, and then calculate for this one here. Once you calculate this one here, you get now your strain displacement matrix. Once you get your strain displacement matrix, go back to this stiffness matrix here to calculate for this one here. The integration is very straightforward. You don't have to perform the integration that you have done for bars and beams. Why? Because you're going to perform numerical integration. We haven't discussed that yet. But that's another form of integration wherein you don't have to perform any analytical integration. Okay? So that's the procedure. To be able to get this one, you need to get this. To be able to get this one, to be able to get that, you need your Jacobian and this value here. Yes? To be able to get your Jacobian, you simply use this equation. To be able to get this derivative of shape function with respect to C, you simply do this one. Very straightforward. All the equations are here, you're just going to follow the procedure. That's why it's numerical. Just put in program to the computer and then put in your values, and that's it, you get your values. Because this steps doesn't change. If, of course, this is just quadrilateral element, of course. If you use solid elements, then that will be a much more complicated solution. But we won't be going through that anyway. So the worst we can do is a quadrilateral element for other solid equations, or solid elements. Probably you can do that in other projects. So I was able now to present to you a bit of what to expect for your finite element 2D. So this is what to expect. So I hope that with the review on the bars and the beams, you have that confidence now to calculate the different requirements for this one. You have sufficient vocabulary to understand what we are talking about. Okay? So, shape function, strain displacement, Jacobian, what else? Stiffness matrix. So, once you have those, it's now easy to solve for your so-called stresses or displacements using the finite element solution F equal to K multiplied by U. Any questions so far? So, if none, then please try to absorb. There's quite a lot of readings here. I won't be talking much about this one. Please have a read. Yeah, I think some of them probably will be useful. Okay? So I'd like to stop there because this one is too numerical. I'd like you to try to absorb it first before we discuss the new topic, or try to solve some examples next week. Okay? There's so many examples in your notes, by the way. I have a few more minutes here. If you try to look at it, this is the step. 24.8.1. See? This is one step solved for the Jacobian. Yes? So once you solve the Jacobian, solve for your strain displacement matrix. So once you solve your strain displacement matrix, you integrate numerically right, so this is now your strain displacement matrix. This now is your plane strain element, so we use the plane strain assumption that this is E. And then after that, you can now integrate numerically, which is this one here. So this example here presents the whole solution. So this is now your stiffness matrix. Yes? So I hope now with this discussion you have now an increased vocabulary in finite element. You should be able to understand the process of determining the stiffness matrix of a plate element.
You know why?
So try to have a look and let's continue next meeting. Okay? Don't worry, it will be easy. I tell you, students, your seniors have done it. After 1 or 2 rounds, it's just just another procedure. Okay? So I'll see you next meeting. Thank you very much.